All right, everyone, welcome to the Colloquium. Our speaker today, Stacy McGaugh, needs no introduction, but here goes. So Stacy was a student at MIT, Princeton, and the University of Michigan, where he got a PhD in astronomy. He did postdoctoral work at Cambridge, the Carnegie Institute of Washington, and Rutgers before joining the astronomy faculty of the University of Maryland. In 2012, we were lucky to bring him here to CWRU, and he's been chair of astronomy since 2015. Stacy works primarily on galaxy dynamics and modified gravity, both on theory and observations. And since he last gave a colloquium here, he has some very important new findings about galaxy dynamics, which he's here to tell us about today. So welcome, Stacy. The floor is yours.
All right, thank you, Harsh. As I was saying earlier, the timing of this is rather coincidental, and it reminds me of some of the deep connections between physics and astronomy, and personally as well. My I won't say, previous century graduating class at MIT included Corbin. At Princeton, I overlapped with Dan Akerib, and would have worked in the Wilkinson lab. But I did some back of the envelope calculations and decided I could work really hard to build a detector, but I wouldn't detect any fluctuations in the CMB. Now the predictions at that time were a little pessimistic for what it turned out to be true, but I was correct that I would not have detected something. And I did want to detect things, which is why one of the reasons why I switched to astronomy, because by that time I had used telescopes and I knew I could make some progress in cosmology that way. So let me, with that framing, share the screen. All right, so I hope everybody can see that now. I should, of course, acknowledge my collaborators. I hope to touch on many things we've done over the course of the years. But I will highlight Pingfei Li, who started as a graduate student in physics, did his PhD with me and graduated a bit over a year ago, and is now a Humboldt Fellow in the IAP Potsdam. Federico Lelli was a postdoc here with me around 2015, 2016. And Jim Schomburg is a long-term collaborator at the Department of Physics in Oregon, and many other people have contributed there as well. All right, now the keyboard has gone insane. Let's try that again. Okay, so I want to give some context for everybody, what we can measure about galaxies, a bit about how we go about doing that. I want to emphasize what I think the important empirical facts are in a way that is as free of theory as possible, and then how that can be used to test theories, and in particular this crazy modified gravity theory called MOND. I would like to say a lot about dark matter, but there's really not time. That's a week's talk all by itself. Now there are lots of patterns in the sky, hence the title I chose. This is an all-sky projection of the Gaia data. Gaia is a European Space Agency satellite operating now to measure the positions of stars all over the sky. And this is a reconstruction of where all the stars are from those data. And this is like looking at a map of the Earth, except now you're looking up at the sky, so you have to imagine this whole thing wrapping around your head. We've chosen a coordinate frame, so the center of the galaxy is in the middle. It's very obvious to your eye where the plane of the Milky Way is. And you can detect these things with your naked eye if you go outdoors in the dark of night. None of us live in a place where it really gets dark anymore, but this is something that humans have known for tens of thousands of years, if not more, because you just go out and see it every night. You can tell that the structure of the Milky Way is flattened. You can tell that there's a preferred direction where there is a center. In the opposite direction, the stars are less concentrated. And if you were really patient and had a micro arc second resolution with your eyes, you could measure your constant B just by staring at the sky. I used to mess with our graduate students by asking them to do that. One pattern that obsesses a lot of us these days is the large scale structure. So the Milky Way is just one of the gazillions of galaxies. So each dot in this all sky projection is one galaxy that is comparable to the Milky Way in size. It's color coded by redshift. The grayish band in this projection is the plane of the Milky Way, where the dust in the plane obscures our view of the more distant universe. But you can see just by eye that there are these big structures, arcs, filaments, voids, so forth. And we now take for granted that that should be the case, but I'm old enough to remember when the CFA stickman was measured in 1987, showing the first really clear large scale structures, that people were shocked that there were any structures that big. We had thought the homogeneity scale of the universe would have been much smaller, a few tens of megaparsecs. And of course, an important pattern that we all take for granted. We had this nice, back in November, celebration of Kepler, with the KSL acquiring a rare manuscript of his. And this is really fundamental to the scientific revolution. Keplers Laws, you can make what is essentially the rotation curve of the solar system. It declines in what we call a Keplerian fashion, 1 over the square root of r fall off, which Kepler enshrined in his third law as the square of the period goes as the cube of the semi-major axis. And that was just an empirical observation. Newton generalized that with his universal law of gravity, and that adds a third parameter, the mass for the solar system. Of course, the only mass that really matters is that of the sun. And these are solar units. So this is solar masses, years, and astronomical units. And this applies now to any exoplanet orbiting a star of any arbitrary mass. So that generalization of a pattern is something that leads to deep physical laws. And so I want to talk about what we see in galaxies that may pertain to that. These are some of the important scaling relations that we find, that these are patterns, but they're not the patterns that Kepler discovered. There's something different. And just like his recognition that planets could be on elliptical orbits was really a mind-blowing generalization at the time. So too was flat rotation curves when it became clear in the 1970s that that was generically true. But there's more to it than that, and so I'll go through that. And these are some important things. We can break them up even further, but these are the 3 basic ones I want to talk about. How we know these things and what we observe. Here are some pretty pictures of galaxies. Galaxies exist over a tremendous dynamic range in mass, but not just mass. Mass is sort of a 0th moment of the whole thing that describes hundreds of billions of stars. So they're spread over some size, some mean surface brightness, a measurable distribution of surface brightness. They have gas. The fraction of their mass that's in gas as opposed to stars is anywhere from nothing to everything. And these are all pretty pictures, so you can see them, but notice the scale bars change by big factors here. So here are the same images all to the same linear scale. And I've labeled the named galaxies so you can keep track of them. There's that little dwarf DDO 154, which you wouldn't notice if I hadn't put the label there, right? It's just tiny compared to this giant galaxy. UGC 2885 happens to be one of the biggest spiral galaxies in the local universe. galaxies are made not just of stars, but also various forms of gas and are presumptively embedded in a dark matter halo. So what you see depends on how you look at them. Here's an optical image, a sort of thing we've obtained with a ground-based telescope. We've spent many years using this particular telescope. This is the 4-meter on Kip Peak and other telescopes up there. It turns out that a good way of mapping the distribution of stellar mass is in the near infrared part of the spectrum, around 2 or 3 microns. So here's a 2.2 micron image from the ground. Really, the best way to do this is from space with the Spitzer Space Telescope. And so most of the data I'm going to talk about come from that. And from the Very Large Array of radio telescopes, looking at the 21 centimeter line, it's the spin flip transition of atomic hydrogen. So we can map out the gas in the interstellar medium. And yes, these are all to the same linear scale. The atomic gas can be traced much further out than the starlight. That's generically true. So now to quantify this, what we typically do is fit ellipses to these images and measure the surface brightness as a function of radius. So that's what this plot is. Each point here represents one fitted ellipse. And the red and blue points are from 2 independent sources of data that are approximately well matched in wavelength, the 2.2 micron image from the ground and the 3.6 micron image from the Spitzer Space Telescope. That's basically the azimuthally averaged radial profile of stellar surface brightness. Now we can assume some mass to light ratio, and that's a critical thing. To do the physics, we need to know the mass. What we observe is the light. We know a lot about stellar populations, so we can make a pretty good estimate of what the mass to light ratio ought to be. And applying that, we can turn this into real physical units, solar masses per square parsec or kilograms per square meter, whatever floats your boat. In this particular case, there are also these black points. These are independent measurements from people who've looked at the velocity dispersions of stars in this nearly face-on galaxy and measured the restoring force to the plane of the disk and used that to infer the stellar mass. That's a much harder thing to do, so they only have a sprinkling of points there. But it's completely independent of our estimate from the photometry and in reasonable agreement with it. So basically, we can measure the gravitational potential by looking at the image. It is what the potential due to the stars is. We can do the same thing for the gas distribution and potentials at linearly. So that's what we expect the force to be. One of the neat things about the interferometric observations from the radio telescopes is that they provide not just that distribution of atomic gas, but also velocities. So you see a velocity field here. One side's coming at you and the other side is going away. And you can fit, again, ellipses and a tilted ring model around here to this formula. Each ring gives a sinusoidal variation as one side's going away, the other side's coming at you. And then again, you can plot the run of that as a function of radius, and that's the observed velocity. And of course, the remarkable thing here is that those become basically flat with a constant rotation speed in the outer parts of spiral galaxies that we've seen over and over and over again. And that's over and above what you can explain with the observed stars and gas. Now, the rotation curves I'm going to talk about, by and large, did not come from me. It is very labor intensive to do that kind of work. And so this has been collected from the literature. Now, we did do some of this ourselves, but the entirety of the database I'm talking about for the rotation curve side of it is really the integrated work of several decades of an entire community of radio astronomers. It's a really precious database because, as I say, that's very hard. So we have slightly under 200 galaxies total, and people say, oh, we can get 10,000 galaxies from Sloan. Why should we care about 200? Well, those 10,000 galaxies from Sloan don't tell you anything about the gas distribution. You have to do this kind of work to get the gas distribution. And so this is much larger than what you get, basically get 0 out of Sloan for that. So this is a huge database by its standard. We've made this available, and it's been very heavily used. This is, those of us who were faculty just had to do our annual reviews. This data paper is in the top percentile of citations for the past 5 years, because everybody's using it, which is great. So now we can engage in this mass modeling exercise. And basically, we're using the measured mass distribution from the observed light distribution to numerically solve the Poisson equation. Now, there are a couple of assumptions one has to make. I mentioned the stellar mass to light ratio. The other thing you have to do is you do need that 3D distribution of density. All we see is a 2D projection onto the sky. So we can deproject it, that's straightforward, but we have to make some assumption about the thickness of the disk. Now, fortunately, there are lots of observations of edge-on disks, and so we know statistically that it's typically 8:1 length to height, but there is some scatter there. You also see modelers sometimes using the exponential disk approximation. This and this log linear plot, that would be a straight line here with slope 1/scale length RD. That's a tolerable approximation for some purposes, but it's not good enough for what I'm talking about here. So we're going to solve the Poisson equation numerically for what we see. A word about the mass to light ratio. This is the famous Hertzsprung-Russell diagram, how bright stars are as a function of their color. Young blue stars over here. These are all data from Gaia. So there's main sequence stars. The sun's around here. And the red giant branch up here and the red clump. For a mature star-forming galaxy like the Milky Way, like most spiral galaxies, one establishes a quasi-equilibrium. As stars evolve, they move up this red giant branch and then they move off it. And roughly speaking, stars are replaced at the rate they evolve away. And what that means is that the luminosity is roughly constant in this near-infrared part of the spectrum. And so that makes it a good place to try to trace the stellar mass. In the past, we've used optical data, and there's a lot of jumping around at the mass to light ratio because young stars come and go on a short time scale, a few 100 million years. They produce a lot of light without representing a lot of the stellar mass. So when we had only optical data to work with, this mass to light ratio bounced around a lot. We just had to live with that. It's much better behaved in the near infrared, even better than we had hoped for. A quick explication of how we apply the Poisson equation. We solve this numerically, and I just want to take you through the approximations that one might make. So the first thing you do is, okay, you have a galaxy of some mass. What would the rotation speed of a test particle be if it were just a point mass, just test particle orbiting a point mass? And I've picked a mass and scale length appropriate to that galaxy I showed you a picture of before. Well, of course, it's not a point mass. So the next approximation you could make is that of a spherical cow. Just assume that you have shells of enclosed mass that match the light distribution. And that gives you that dashed line. And the reason it's very different from the point mass at small radii is because it's not all concentrated at small radii. You have to integrate out a while before you enclose all of that mass. And then once you have close that mass, then you see the Keplerian fall off and they match up. Spiral galaxies are not spherical cows. They are flattened rotating mass distributions. And it's just a geometrical effect that the equivalent flattened distribution rotates a bit faster than the equivalent spherical mass distribution. So this is sort of intro grad galaxy dynamics. And so this is the thin exponential disk approximation, assuming that exponential disk formula, you can solve it. And this is sort of the last analytic thing you can do, and you meet Bessel functions, and a lot of people's eyes cross at this point, but you can, at least in principle, do it analytically. And you notice there are important differences between this and the spherical cow. The geometry does matter at sort of the 20% level. The next approximation is say, okay, disks are not razor thin, so you can allow some finite thickness, and like I say, 8 to 1 is typical, and that goes back in the direction of the spherical approximation, but it's not all the way there. And then what we do is actually feed the run of azimuthally averaged surface densities to a program that numerically solves the Poisson equation and gives us that blue line. So that includes all the bumps and wiggles and features and whatnot that are there in the light distribution. This is just for the disk component. One could do better. One could make two-dimensional models that include variations with azimuth. So if there's a bar or spiral arms, things like that, you can make a three-dimensional model. You can also consider non-equilibrium effects, which are almost always present at some level. But as soon as you do this, then you're introducing a bunch of extra parameters that are very hard to constrain. So that is fun to consider in a modeling one galaxy at a time kind of way. But if you want to look at 200, you can't really get past the level. So we're going to do the most sophisticated thing we can while pretending the galaxies are azimuthally averaged and in equilibrium. Okay, so what are the rules of the game here? One, as we've known for a long time now, rotation curves become approximately flat. They're not dV/dr equals 0.000. But there is a very long and often indefinite period over which they're very nearly constant rotation speed. And this is the, one of the formative events in the establishment of the dark matter paradigm. They do not fall off in the Keplerian fashion that's predicted from the mass models I was just talking about. So you need something extra there. It's not just that. So at the time that we developed the dark matter paradigm, that was basically the only input. We needed something extra. There's more to the story, and the patterns in that need to inform the theory. So sort of the next thing up is the Tolley-Fisher relation, that the amplitude of that flat rotation speed correlates with the mass of the stuff that you can see. So a big galaxy like UTC 2885 rotating at 300 kilometers a second. As you go down to lower mass galaxies, the rotation speed gets smaller and smaller. You get down to little dwarfs like the ones I've studied, and you get down as far as 20 kilometers a second. It's roughly, I guess, VOP is down around 15 kilometers a second. So big range in velocities there. So now each point on this graph is one galaxy, and it plots baryonic mass here. That is the sum of stars and gas, basically all the mass that we see, against that flat rotation velocity. And this is a good correlation over about 5 decades in mass. The scatter is remarkably small. If you're used to doing precision experiments, this looks maybe messy to you. For an extragalactic astronomer like myself, this is unbelievably small scatter. You just almost never see that. And you can do the error budget, right? You see error bars on there. You can calculate what the scatter should be. And it is basically what it is. That is to say that the amount of scatter you see there is consistent with the underlying relation being essentially perfect without scatter. And then, everything after that is just observational uncertainties. We can put an upper limit on that scatter, which is basically around what we expect variations in the stellar mass to light ratio to be. So it's as tight as it can possibly be.
So just a quick clarificatory question. What maybe we can take this up later, but what do the two colors represent?
So I've split this up in this case by whether a galaxy is dominated by its stellar mass, where the red we've measured with the Spitzer Space Telescope. So we've just integrated the light there, assumed the mass to light ratio based on the stellar population models. And that's where that mass comes from. The blue points are galaxies that have more gas than stars. And so that's basically driven by the flux that we observe for the 21 centimeter line. There is no freedom in that conversion for gas mass. There is no mass to light ratio. We understand the physics of the 21 centimeter spin flip line. The Einstein coefficients say that one atom does this once every 11 million years or something crazy like that. But of course, there's gazillions of atoms out there. And so we can basically count photons and say how much mass there is. And that's important because that basically gives you an absolute scale here that is independent of the population mass to light ratio, which is not true for the star-dominated galaxies. I can move those up and down by playing games with the population synthesis models. This is our best estimate, and it also gives you that nice continuity from one to the other, which timing-wise, I did the blue before the red, so it was really nice to see that the population models seem to be getting to a consistent answer. It doesn't put some kind of feature in here, which is easy to do if you make an unwise choice for the mass to light ratio. I told myself I was not going to say anything about cosmology here, but I couldn't resist. One of the absolute fundamental measurements one can make in traditional cosmology is distance scale. One can take that relation I just showed and use it to estimate the local Hubble constant. We did this a couple of years ago now, and we get 75 kilometers per second per megaparsec. This is the calibration data. It has a mix of, to calibrate this, you need to know the distance by some independent method. It has both Cepheid and tip of the red giant branch calibrations, and there is no meaningful offset between those two. There's some debate about that. We just don't see that. And we get a number for the Hubble constant, which is consistent with what the supernova people get. Basically, everybody else gets too. So Brent Tolley, who this relation is named after, is also getting numbers very consistent with that. With a much larger sample, so its statistical error is smaller, but with a less accurate velocity estimator, so the systematic uncertainty is larger. But it's 75, it might be 72, it is not 67, it's just not. Now, the thing that's interesting for whatever physics is driving this relation, and that's really not clear, but an important thing to know is that there is just no residual from this relation with anything, including from scale length. So at a given mass, there are compact galaxies, there are spread out galaxies. And so that's what this residual here shows, is the relative size of the galaxy, small or big, at a given mass. And you would think that would map into the velocity naively by that dotted red line. That's just the slope you would expect. In fact, that was my prediction. I predicted this is what happened when I first studied low surface brightness galaxies, because there were objects of the same mass but different radius. That was wrong. The data did not get that memo. There is absolutely no hint of any dependence on the size of a galaxy. And that is weird because the velocity is a combination of both the baryons and the dark matter over the range where we measure B flat. How much is which depends. And yet the rotation curve stays pretty flat while one component is falling off and the other has to be rising up. There is a fine-tuning problem there that some people would call the disk halo conspiracy. I would say it's actually worse than that. But I will leave it as an exercise to the listener to determine if one considers this to be a fine-tuning problem. I do. Now, there's more to it than that. that was just the outer flat velocity and the total mass. We also know the entire distribution of the stellar mass, and there are various ways to quantify that. We know the entire shape of the rotation curve, and so this is what we had in the 2000s. So this is from a review in 2012. Rotation curves with the colors binned up by surface brightness. So blue, the lowest surface brightness, the red, the highest surface brightness. And you can see there's a bit of a rainbow there. But it's not a perfect rainbow. There are some green things above the red things. And that's basically the sort of mishmash that you expect from the scatter and the mass to light ratio that I mentioned before. That's unavoidable when you have optical data, just because the optical light comes and goes with the stochastic history of recent star formation. When we got all this infrared data, it became this. And this was incredibly satisfactory to me, because I could see it was there in the optical data. And we had moved to working in the infrared because we expected, based on what we know from stellar populations, that it would give you a better idea of the stellar mass and measures the stellar surface density. And that cleans up this rainbow, right? It's almost a perfect rainbow now from the bluest to the reddest colors, right? So that was expected, and I didn't even expect it to be this good. There's always going to be some mixing, because there's always going to be some scatter in the mass to light ratio. This just reduces it. So you can see this. So there's more to explain here than just the flat part, and there's this whole range of shapes of things to explain. And the dynamics, measured by the velocity, clearly knows about the distribution of stellar mass, not just the total, but the shape. Is it spread out? Is it compact? So this is what leads us to the radial acceleration relation. And this sort of combines a lot of details into a simple thing. So I want you to appreciate both how we get there, but also how many complex features go into it. So here's a Spitzer image of one of the galaxies. It's a fairly high surface brightness galaxy, nice big bulge. That is that bright peak right in the center there of the surface brightness profile. It goes out, gets to lower surface brightness. You see some features. This is called a lens feature, that sort of shelf there. And then a quasi-exponential disk further out. So that dashed line is an exponential disk fit. But we're not going to use that. We're going to solve the Poisson equation numerically for that mass distribution to get the predicted accelerations for, just basically given this mass distribution, what does Newton say should happen? And then we can independently measure the rotation curve. And so that's what's here. This is basically, you can get the centripetal acceleration from this rotation curve. That's the force that you need to keep an object in circular motion. So the baryonic rotation curve is the blue line. The observed line is that. So that's the difference, and that difference is why we have a dark matter problem. So here are a few galaxies now. Again, rotation curves, the blue line's what Newton predicts for the observed distribution of stars and gas. The points are the observed rotation curves. And you can see these are three very different galaxies. There's one galaxy that has a big central bulge that provides a lot of the stellar mass. That explains pretty much everything at small radius, but falls off later on. A sort of an intermediate sort of brightness galaxy where the stars are important at small radii, but again falls off. And one of these low surface brightness gas-dominated cases where the stars produce almost none of the restoring force, but the gas also, and there's a huge discrepancy at almost all radii. Maybe not at the very smallest, but everywhere else there is. And so you just look at it in that traditional velocity against radius kind of way, and there's no obvious pattern. However, and believe me, I've been through all sorts of patterns with frequency and all sorts of scales you can imagine. The one that matters is acceleration. So the rotation velocity maps to g-obs. That's basically the centripetal acceleration. And you can plot that against what's predicted by Newton for the observed distribution of baryons. So that's the observed versus the baryon predicted distribution. And this galaxy gives you that black line. If there were no funny business, no dark matter, no whatever, then Newton would work and you just have a straight line here. And you do at high accelerations, that's right up here. So do the same thing for this galaxy, and it kind of extends this relation to lower accelerations. And again, for the low surface brightness galaxy down here. And now you can see these are all sort of falling on the same line. That's sort of a pattern. So we can put together all of our data and we can't really tell the difference. So this is what I call the radial acceleration relation. What you see is not what you get in the Newtonian sense. That dotted line is the purely Newtonian expectation. But what you see is predictive of what you get. So much so that you can just fit a function. This is one we chose that works. You could choose other functional forms, but basically that line is fit to those data and it goes right through it. So it bends at some characteristic acceleration scale that's about 1 angstrom per second per second. So that's about 1 part in 10 to the 11 of what we feel sitting here on Earth. And again, the scatter is about what you would expect. So I've forgotten now which is the calculated and predicted scatter, but you can see they pretty much match. Right? You go through all the uncertainties, and I'll come back to that. Like I said, so the observed scatter is that black dashed line. Doing the error budget, the red line is what you expect the scatter to be. So basically, this is another perfect relation. There's no obvious need for intrinsic scatter here. Of course, you can only put an upper limit on it, but that's what it is. Now, this is not new to me. I've been working on this for over 20 years. So I went back and I dug out what I had first published in the previous century. At the time, I was working on low surface brightness galaxies, which turn out to have low accelerations. And so there's a big concentration of points here. And I should mention that I thought this was new when I did it in 99 or 98. I found that Bob Sanders had said something similar in 1990. So I wasn't even the first to say this. And so I spent a lot of time improving and generalizing the data. And by 2004, this is what we had. Now, this in some sense may look worse to you, but it is in fact better because there's a lot more galaxies, a lot more points, and they're just all piling on top of each other. But you can also see the concern here that there are sometimes you just get the mass to light ratio wrong. And so you can see individual galaxies as streaks here. And that's what the price you have to pay when you're using optical data. The mass to light ratio bounces around. So at this point, we started working with Spitzer data to try to improve this, and it took basically a decade to get here, but that is the result. So it was worth it. Took a while, but basically each one of those points is one resolved point along the rotation curve of 153 different galaxies. And you can barely tell the difference. Now, this is actually better than I expect. I still expected there would be some outliers that you could see by eye, and that's not really true. There's one weird one there, okay. There's one weird one here. But by and large, things just pile right on top of each other. So this worked better than we expected. And there's the scatter budget. I was getting ahead of myself. But that's basically the big uncertainties are just, there's some irreducible scatter in the stellar mass to light ratio. The population synthesis people argue about what that is, and most of them tell me it should be bigger. So in some sense, we put a limit on that. Not all of them do, but some of them do. The big uncertainty here is distance uncertainties. But basically, it's just All the scatter is just that, scatter. Okay, so now what good is this? What you see is predictive of what you get. So you can use this functional form we fit to take the predicted baryonic rotation curve and map it to the total rotation curve. So you can fit one with the other. Basically, you can look at something and predict what its velocities are going to be. In this case, things are very Newtonian in the inner part. It better work out, but there's a modest correction that gets bigger as you go further out because the accelerations are lower, and this functional form diverges systematically from the Newtonian prediction to lower and lower accelerations. That's what's happening as you go farther and farther out. In low surface brightness galaxies, the things that I've worked on most of my career, the accelerations are low everywhere. So this correction is large everywhere. And yet you have these curiosities, like there's this pronounced feature in the gas distribution of this galaxy, and that is reflected in the kinematics. That makes no sense in terms of this being embedded in a dark matter halo. This sort of feature is very natural to a thin rotating disk. It is completely anathema to a quasi-spherical halo supported by random orbits. You just can't have it. Again, that's graduate dynamics 101. And yet, for some reason, it works to scale this up according to that formula. For a review, was it last year, year before? What is time anymore? I actually set myself the exercise of saying, what would we predict? No fitting of the mass to light ratio, just making our best guess for that number and fitting to the rotation curves, not fitting, mapping the rotation, predicting the rotation curves. And these are the residuals. The colors represent the quality of the data. The best data are blue, and then green, and then the gray, which have the big error bars. And so you can see the expected trend that the worst data deviates more from the prediction. But then down below is the input mass to light ratio. Most of these are just disks. We did allow for a separate mass to light ratio for the bulge component, so there are a few galaxies where that's important. And as a person who's worried about the mass to light ratio of stellar populations for a long time, this graph makes my head explode. There's no scatter. There has to be scatter. So all that scatter appears up here. If we allow that one parameter to fit, well, then you minimize that scatter, and it comes out in the scatter of the fitted mass to light ratios. So is that number reasonable? And the answer is yes. From the stellar populations, that black line is the mean that's expected, and that band is sort of the 1 sigma spread that you would naively expect. Now remember, there are observational errors here. The things with really big errors I've plotted as gray points. With not terribly huge errors I've plotted as blue points. And I've suppressed that because then it's just a forest of error bars. So the scatter in the blue points is both that intrinsic scatter and the mass to light ratios plus the observational errors. Basically, that's as good as you can hope to get. And there are always outliers. Astronomy, there's always something weird. Now, each of these relations I've talked about involves a particular acceleration scale in the data. This is just in the data. I haven't really said much about theory so far. One can construct an acceleration scale from the Tully-Fisher data, and that is that solid line going through the data. Federico Lelli just published last month a nice review in Nature Astronomy of that. So that's one indication of this acceleration scale. The radial acceleration relation I just showed you. It's basically the acceleration scale is where it bends. There's also something in the inner surface densities, which I haven't covered, which I call the central density relation. It bends at a critical surface density scale, and that's related to acceleration by Newton's constant. And these numbers are all the same within the uncertainties. They don't have to be. And this is a special scale. So this is a really tiny scale. All the galaxies data cluster around this really tiny scale, about 10 to the minus 10 meters per second. And that is completely out of our laboratory experience, completely out of our solar system experience. Here are all the planets in the solar system, many decades higher in acceleration than galaxies experience. Here we are on the surface of the Earth. Here's the periapsis of the Hulse-Taylor pulsar. That was the first indirect indication of gravitational radiation, the decay of that orbit. Way up here is the first LIGO detection of an emerging black hole pair. That was basically the centripetal acceleration of the last stable circular orbit as it ramped into a merger, about 10 to the 11 meters per second. And kind of the highest acceleration one can imagine is the surface of a neutron star that's on the brink of collapse to a black hole around 10 to 13 meters per second. And meaning of acceleration in our conventional sense that basically ceases to exist at that point. But over all of these decades, there's no hint that our understanding of gravity is wrong. But then we suddenly need dark matter at this very small scale. Which brings me to Mond. So like I would say, I would like to talk a lot about dark matter and what you can't predict here. There's just not time for that. And so I will tell you about something that people mostly don't know about, which is this crazy sounding theory by Monty Milgram, which he invented to make rotation curves flat. That was the animating purpose, just like we invoke dark matter to explain that. But he did it instead of invoking dark matter by hypothesizing that the force changed at some small acceleration. Most of the data that I just told you about didn't exist when he did this. He just posited that, okay, everything's Newtonian above some acceleration scale that happens to be about 1 angstrom per second. That number has to be measured. He knew it had to be small and of that order, but it's not predicted by fundamental theory. But the asymptotic limits are. It basically looks like Newton at high acceleration, and at low acceleration, it goes to this really weird effective force where you multiply what Newton predicts by this new constant, A naught of the theory, in quadrature. And you look at that and your head should explode because this does not conserve momentum or energy, and it's just horrible. So there are two possible interpretations of this idea. You can either modify inertia, that is, break the equivalence of inertial and gravitational mass so that gravity is still the same, but F no longer equals ma. Or you can leave that alone and you can modify gravity, which most people think is less radical, though they're both pretty crazy sounding. It was a long time that, well, it wasn't a long time, it was pretty quickly that Bekenstein came along and used an action to derive a modified Poisson equation that does, in fact, obey all the necessary conservation laws. Now, this is a generalization of Newton's kinematics, but not of general relativity. That's still an outstanding question. But it is a conservative force law in the same sense that Newton is, with these asymptotic limits. And so this is really what it predicts, that everything is Newtonian at high accelerations. And then there's some transition around this special acceleration scale. And then it asymptotes to that limit. And these different lines are different interpolation functions, this mu here, that basically just paste together these two limits. So the limits are fundamental to the theory. How one gets from one to the other is not. There's no theory that says that you have to have this function or that function. But this is the sort of range of things that people have considered. And we hope to goodness that it is smooth and continuous and well-behaved and all that sort of thing. Now, I mention this only because it predicted all the things I talked about. In 1983, Milgram wrote down all the things I just told you. Low surface brightness galaxies, what I've been studying, were basically unknown at that time. And he made very specific predictions for what they would do. And I had not observed low-Earth brightness galaxies to test his theory. I was interested in them. But if I had wanted to build an experiment to test that theory, that would have been the thing to do. And I've given little gold stars to the things that were truly a priori predictions, things that he said then that came true. Silver stars are things in the same category of the prediction of the precession of Mercury's perihelion by general relativity, things that have to be so, but were already known at the time. And then these brown stars involve some kind of fitting. But there are also a bunch of things here that we did not expect this to be the case in the dark matter paradigm. And there's some things that make no sense in the dark matter paradigm. I don't have time to talk about that. Now, I've heard all sorts of myths over the years about what MOND is and isn't, and having bothered to learn, it's kind of amazing what people will still say about it. So this is a paragraph from a 1998 paper, where at the time, one of the popular myths was that MOND was guaranteed to fit rotation curves. So what we did was we took a pair of galaxies that were indistinguishable in Pauli-Fisher, same phi-flat, same total mass, but we swapped the mass distributions and tried to trick it. And the answer is you can't. So the mass distributions were different. You have that one simple equation, and there's no way you can adjust your one free parameter, the mass to light ratio, to map one galaxy to the other, even though we gave it a good chance by picking a matched pair in terms of total mass. You can make the same fit with the dark matter halo, and you have enough freedom there to do that. Dark matter paradigm will not tell you that you've intentionally got bad data there. So this is raises deep questions in fundamental theory, one of which applies to the equivalence principle. You know, I'm old enough to have been taught that the equivalence principle is that inertial mass is identical to gravitational charge. If you go and read the review literature now, so I'm citing Cliff Will here, you get a more complicated picture. So there's weak equivalence, University of free fall, lead falls the same as feathers, that's not in doubt here. There's strong equivalence, which isn't just that anymore. It's weak equivalence plus Lorentz invariance plus local position invariance. And then there's the Einstein equivalence principle, which makes an exception for gravitational experiments. They happen to think self-gravitate. So that's a slightly weaker statement than a strong equivalence principle. And this is the piece that MOND breaks. You violate the strong equivalence principle, but not the weak or necessarily the Einstein equivalence principle. And the thing that breaks there is position invariance. Because what matters is the total acceleration. You get into this deep MOND regime, how much of a boost you get depends on the acceleration from all sources, that internal to the object, and that from something further out. So here are all the formulas and situations that can arise. I'm running out of time, so I'll just say that there are matched pairs of dwarf galaxies in orbit around the Milky Way and around Andromeda, where we can get pretty good data. And the formula that applies in MOND depends on whether this external field from the big host is negligible, or if the dwarf is up close enough, and you can find matched pairs where they basically look the same in terms of total mass, but their dynamics should be different depending on that because of this violation of local position invariance. And there is evidence for this. I'll skip through that. Here are the velocity dispersions measured and predicted for all the dwarfs of Andromeda. This is work I did in 2013 with Milgram. It's the only time I've collaborated with him. It's not quite true, but only real time. Basically, you can see a bunch of measurements and a prediction. And in all cases except Andromeda 5, the predictions are consistent with the measurements. And okay, the measurements really don't test it in a couple cases here. But Andromeda 5 is the only problematic case. In the other case, you can do this over and over again. And if you try to do this with dark matter, you can't. Believe me, I tried, but the relation between mass to light is extremely nonlinear in present dark matter theory, and to the point where basically the light should not be predictive of the velocities. Yet it is. And so, oh, there's my little gold stars. I wanted to say that because, again, people say this is not a predictive theory. Those gold stars are all individual cases where the prediction was made in advance of the data. The others are silver stars, really, because, you know, I don't really have the freedom to fix this. That's what it should be. Andromeda 4 there is missing. That's also a gold star because it was first identified near to Andromeda on the sky. And Milgram looked at the velocities and said, oh, no, that's got to be a background object. The velocities are much too high, so the mass has to be higher. And people later went out and measured the distance independently, and sure enough, it's not a satellite, it's a background object. So there is some evidence for this violation of position invariance. Oop. All right, fine, we'll just keep going because I'm out of time. One can do that for large scale structure too, but like I say, I've used all the time, so I will just flash up the conclusions and say, look, empirically, galaxies obey these strict kinematic scaling laws. That's what I have worked on. Right? I did not discover that rotation curves were flat. I did not discover the Pauli-Fish relation. I did point out that it was baryonic mass that was the important thing there. And I did work to identify the radial acceleration relation. Those are all true empirically. It's not my fault that Mond is the theory that predicted these things, but it did, and nobody else did. And remember, as I said earlier on, I predicted that the low surface brightness galaxies would fall off of the Pauli-Fish relation. That's sort of what I expect from any proper Newtonian theory. So I'm happy to say I'm wrong when I'm wrong, but I don't feel like I have the liberty to say that Milgram is wrong when he gets these many predictions correct. It really seems like it would be a bit of a miracle. In fact, there is a line of reasoning in the philosophy of science that is exactly that. It would be miraculous for a theory to get this many predictions right and not have something to do with the underlying reality we're trying to say. Which is all to say, none of this makes any sense. I don't understand how any of this can be true, but that's where we're at. So thank you for your attention.
Yeah, well, I wish we could, keep going for another hour, but
yeah, there's as I warned you, it's hard to get through it.
Yeah, but I think we should go over to as usual. What we'll do is we'll do a few questions in the formal session, and then maybe we'll break up we'll turn off the recording and have 10 or 15 minutes of conversation. So I'd especially like to invite questions from students or general interest questions in this session, and then formal we can go for more specialized questions.
I may have missed this part, but could you talk a little bit more about? You didn't. I don't think you talked about like Einstein. Did you talk much about Einstein's you talked a bit about like his equivalence principle and stuff like that, and how this matches to that. But why? I remember you mentioning something about how this fits into a regime. There's like a scaling regime where these observations fit into Newton's theory, and then where they don't. But you didn't mention, I don't think, like relativity fitting into there at all, did you? Or
no, not really, and that's
okay.
For want of time, and also for want of theory. So it's not really clear what the proper answer is. But they're in very different regimes, right? Relativity is what happens as velocity approaches the speed of light, and MOND is what happens when acceleration gets way below this tiny acceleration scale. So they happen in really extremely different regimes. And so, for example, in the case of modified inertia, that seems completely anathema to general relativity. It violates the original equivalence of inertial mass and gravitational charge. On the other hand, once you say, okay, maybe that's true, what does it do to GR? Not obvious. It's theoretically really unpleasant. It's not obvious you have to change anything else. And so one, to discuss this, finds oneself wrestling with these really deep issues. And lots of people have tried to construct extensions of general relativity that encompass both general relativity and Mondian behavior. Most have tried and failed. The most recent promising effort is from Skordas and Zlosnik, something they call RelMond, which has lots of empirically nice properties. It gives a good fit to the cosmic microwave background, gets gravitational lensing right, doesn't violate the propagation speed of gravitational waves. But yet, whether that's actually a right theory or not is I don't know.
All right, thank you.
Okay, I see we have a question from Sophia. Go ahead, Sophia.
Hi, thanks for the talk. Oh, we have an echo. Well, I was wondering, in all of your years of working on this research, what has been the most surprising thing to you that you found?
Well, certainly that MOND got any predictions right. So in the previous century, I was working on these low surface brightness galaxies, and I had made a couple of predictions for them. One, I mentioned that they should shift off of Tully-Fisher, and the other was that they should be distributed in the same sort of large scale structure, but not as tightly. The amplitude of the correlation function should have been weaker. That prediction came true. And so I thought I understood things, and then I got around to testing the Tully-Fisher prediction, and it did not come true. So that was a deep shock. And the deeper shock came when I realized almost by accident that MOND had predicted exactly what I was seeing. And that accident was a chance meeting in Middle Earth. I happened to be a postdoc in Cambridge at the time when Milgram came through and gave a talk. I was struggling with this. I said, I think it's a fine-tuning problem to get low surface brightness galaxies on the same Tully-Fisher relation as everything else. I encourage everybody to try to think that through for themselves. And I had spent months pounding my head against this problem, and every time I thought I had solved it, it was I realized I had introduced some tautology that made it so. And then Milgram came through, gave this talk I almost didn't go to because like, oh, modified gravity, he wants to hear about this nonsense. And then in a few lines on the board, he derived what I was seeing. So that was by far the biggest shock of my career.
Well, I guess I had a question. I have several questions, but I'll ask one of those right now. Every now and then you hear, especially in the popular press, about these exceptions, that seem not to work. And indeed, you mentioned, with Andromeda 5 as well. And how are we to interpret those? If we, are those like, is it just in the modeling and the observations that something goes wrong, or? I guess what I'm talking about are the galaxies which appear to have no dark matter.
Right. So there are always exceptions, as I say. Currently, there's a lot of talk about ultra diffuse galaxies that fall off Tully-Fisher, for example. There are lots of things that can go wrong there. So a recent blog post I made discussed one of those cases where I think basically they get the inclination wrong. And if you just look at the data, it's like, oh, there's no way they could get it wrong by that much. And actually, yeah, you could. For a good 20 years, I very dutifully chased down every one of those things and almost all of the exceptions went away as the data improved. And I've reached a point in life where I don't have the time or energy to do that for every single exception. But my experience with literally hundreds of cases is that they don't always, Now that's not to say there aren't real problems. So one persistent problem I guess I have to share my screen again. Is clusters of galaxies. I think that is real and that is persistent. And how bad it is depends on how you look at it. So this is the radial acceleration relation over a really large dynamic range going up to the solar system. Right, here we are. I haven't tried to extend it up to merging black holes and so forth, because then the interesting part gets tiny. But so you can see the galaxy kinematics there. You can see some recent galaxy lensing data. And the clusters are these X's, and they all sit systematically off and above the relation, or to the left, depending on which way you want to look at it. And that has been persistent. And the amplitude is about a factor of 2. And so this is where it's really a matter of attitude. So if you really hate this theory, then it's clearly wrong here, and so you don't think about it anymore. If you really like this theory, then what's a factor of 2 in astronomy? I don't really know which way to go with that, but I do know that there are a lot of modelers of dark matter who get within a factor of 2 of this relation and claim victory. And basically, they miss by as much as the clusters do. So, that's something we all have to figure out how to deal with. There are certainly other problems as well, the theoretical ones looming large. But I guess to me, the exceptions are just an excuse to miss the forest because of a few outlying trees. Right? There are hundreds and hundreds of galaxies. That's the forest. These relations are the forest. Sure, there are outliers, and there always will be in astronomy.
All right, well, I think this might be a good place for us to leave the formal discussion and end proceedings. So let's thank Stacy and yes.
Yay, I'll give myself applause because I can't hear any of you.
Right. Well, you're one of the few who's have we can hear, so yes. All right, I'm going to stop
Thank you for
recording.
your attention.
Yeah, but please